Hi, I'm Abby Dove. I'm a postdoctoral researcher at the University of Central Florida. I work with Dr. Josh Caldwell. We do a lot of experiments that involve collisions in microgravity environments. And so I titled my slide Collisions in Space with an asterisk because the asterisk is, usually when you think of collisions in space, you think of really big events, right? Like planet destroying events or asteroids breaking up and things like that. But what we want to look at is actually really small events. Little tiny particles or centimeter-sized objects that hit each other and stick together. So, because I'm a scientist, I have to give a little motivation for my research. Why do we care about collisions in space? Well, it has to do with how planets, moons, and rings form. So, when early on in solar system formation, right, you have it's called a protoplanetary nebula. And it basically just means you have a lot of gas and dust orbiting the central star. And when this happens, somehow, right, you form planets in these environments. And there's actually some questions as to how planets form. There's these barriers you have to get over in terms of coming from really small dust particles to big protoplanetary objects and then planets, right? So there's some barriers you have to overcome, and we think that some of our research will help us understand how you get from the really tiniest small dust particles to bigger centimeter and decimeter sized objects. So this is the case, for instance, this is Fomalhaut. It's been imaged. It's an actual protoplanetary disk around another star, and you can see this is all a signature of dust around other stars. And this is also applicable to the Saturnian system, which has the rings around it, right? So Saturn has these gorgeous rings, and actually most of those rings are driven by ice and rock that occasionally slam into each other and either break particles up, or occasionally you have things building up bigger particles. So that's why we're interested in this. How do planets form, and how do the Saturnian ring systems change, all of that. But so, how are we going to study this in a microgravity environment? Well, our lab has some history of doing different experiments that look at collisions in microgravity. So in the past, there's been an experiment called Collide that flew on Space Shuttle. So this is sort of the housing for the Collide payload, and there are some little small, they're called IBSs, little box units that have an experiment in them. And then this structure, called Prime, has been built to fly on some of the suborbital parabolic flights. So each of these boxes right here is a different payload. And in all of these experiments, we can zoom in on some of these experiment boxes. We have sort of a big experiment box with different mechanical parts in it. And then generally we've had like a tray of dirt or lunar simulant or something like that in the bottom that you have an impactor that hits into it. And you study the ejecta that comes off of that, and that helps you understand how, when you have a particle hitting a larger object, what happens to the ejecta that comes off of it, or if the particle, marble or something, might stick to the larger object. And so the background of all my slides is sort of a video shot from one of these experiments where you have this ejecta curtain that comes up after you've had an impactor hit into this tray of dirt. So one of the things that we've been interested in doing is trying to get this smaller. So there's all of these new opportunities for companies like NanoRacks and other companies that are building these small payloads. But the problem is, right, these are not really small payloads. Even for this prime box size, the box itself is about a foot tall, right? And that's bigger than any NanoRacks payload. So we are interested in building a really small one. And so this is to scale, actually, where we have, again, the prime rack, this Collide experiment that went on Space Shuttle. And then this is the size of a NanoRacks 1.5U unit. So this is about 6 inches tall and 4 inches in the other two directions. So this is our sort of next generation, and this is the payload I'm going to talk to you about right now. So we were awarded a proposal through Space Florida and NanoRacks to build this very small payload and look at how particles collide, or how particles collision occur in microgravity. So this is that image I just showed you. So this is our payload. I work in a lab that's mostly undergraduate students, so undergraduate engineering students have built all of this, and it's actually still in progress. We are planning to go up on the next SpaceX flight. For the NanoRacks payload, we'll go up on the next SpaceX flight. So I'll go now through our payload and what we're looking at. So you can see here, just from the top down, there's a mirror, and I'm going to explain each of these in a little bit more detail. We have a camera. We have an experiment tray, and you can see in that experiment tray there's sort of these little chambers that are milled in. We have an electromagnet down under that experiment tray and some springs that this tray sits on. And so I'll describe all of this in a little bit more detail. But again, remember that this is in sort of a, when we're designing these experiments, it's in a really small payload, and you have to figure out how to have your lights and your camera and all of your data collection all in one small unit. Oh yeah, and there's a student in the background, just for evidence that we work with students. So this is the sort of the bottom of the tray. You can see we sort of have these stabilizing pins. One of the things we had to consider when we were building this is you're not just thinking about what's happening when it's up on the station, right? It has to get there. And so when we launch this thing, we have to be able to sort of lock, it's sitting on springs, so we have to lock the tray down and make it stable so that when it's going through all the vibration, when it's going up to space station, it doesn't completely destroy our experiment before we even get there. And this is actually going to go for vibe testing later in the month, so hopefully, I'll get back to you, but hopefully it survives and all of these actually work as they're supposed to. But so like I mentioned, we have the simulant tray. It's going to have all sorts of different little simulants in it, and I actually brought some examples of some of these things. So I have an example tray and a camera that I can show you guys later if we want to do one of the unconference sessions. And then like I mentioned, there's these springs and electromagnet down the bottom, and you say, why would you put those in there? Well, in order to simulate collisions, right, we have to create collisions. And if it's just sitting up in microgravity, if we just had it sitting there, maybe the station shakes enough that you get things moving around, but sort of nominally, they're not going to be moving around. So what we do is we have a little electromagnet that sits below the tray. Every once in a while, it's activated, so it pulls the tray down. But then when the electromagnet's turned off, it's sitting on springs, so it bounces up and down. And you can create some motion that way. And we have these trays are really narrow so that you'll sort of get a little motion in the vertical direction, but mostly you'll get it sort of along, you get these simulants colliding in the tray itself and moving around. And so then what we do is we need data, right? So how do we get data? For the most part, for these experiments, we use video data. And so what we need, especially for this, is a very small camera, right? So we have this little camera here, and it's a very tight space. And it turns out if you put the camera up at the top of the box, looking straight down, you don't really get a big enough field of view to see your entire experiment tray. So what we had to do was put the camera down here, looking up at a mirror, that then looks at the entire experiment tray so we can see all of it in action. You can see here, we use a very high-tech TV to do some of these initial video analysis to see what our tray is looking at. And it's actually a little bit wider than the field of view you can see on the TV. But so you can see here, we can see all of the little chambers in our experiment tray. And one of the key things for this is that it's actually a pretty low power experiment. So we needed a camera that had low power, but sort of a large field of view. And for our research, we're sort of interested in things that happen in really small timescales. So we need a high recording speed. And so 60 frames per second is sort of the lower end of what we'd like to do, but we're working with that for now. And so this is just an example snapshot from a camera. And we actually used this, we got this snapshot using some Arduino software. So for the actual experiment, we're provided a board through a different company called Celestial Circuits that's working with nanoracks. But we have done a lot of our testing with Arduino software. There's a lot of just sort of example code out there actually already on the internet for using some of these little cameras that we're using with Arduino software and figuring out how to take snapshots and things like that. So this is an example, like I said, we have some little simulants in here. Obviously, it's just sort of sitting there right now. But we can actually get some good data and hopefully eventually record the data to study how these little particles collide when they're moving around up in the microgravity environment. And the nice thing about this is that it'll be up there for 30 days, which for us is a really long time to just sort of be able to repeat this experiment, right? So we'll be able to make things collide, download the data, watch it again, and then watch it happen over and over again and see if we get structures building up, if we get things mostly just breaking apart. And we have different types of simulants that we're putting in so we can see how their properties are going to affect how they stick together or break apart. And I believe, so this is sort of the overall science goals of what we're trying to learn. And mostly it is about sticking, rebound, and fragmentation. So like I said, if things stick together or break apart, and that's sort of the big science drivers for what we're interested in. And this is sort of a very small experiment, right? But it gives us a good proving ground to say that we can do these things up on the space station and hopefully build up slightly larger projects or give us ideas for different ways to modify some of these experiments for space station use in the future. So I'd like to thank Central Florida and Space Florida and nanoracks for all of this and just a final view of the payload that we're developing. Thank you.